Welcome to this tutorial and review of the Visualizing Acceleration quiz and opportunity for you to earn some points back. I plotted these data points here in an Excel graph and you see the result. We're just looking for good graphing basics, right, on number one. So did you give axis labels and units? Did you give a title? Did you plot them correctly, which should yield a pretty linear trend? In number two, you were simply asked to extend the line beyond the data points, right? So you could get a trend here. And then number three on the next page has us describing the motion in words and also drawing an FBD. So let's look at the graph and describe the motion in words. Contrary to your intuition, right, the slowest you can go on a VT graph is not the bottom of the graph. It's the middle. So anytime the trend approaches the middle, as it does here, it must be slowing down. And then the fact that all of these numbers are negative velocities, right, means it must be going in the negative direction. Well, which way is the negative direction? Let's look at the drawing. The negative direction is toward the detector. So the cart must be moving toward the detector as all of the velocities are negative, right? And just as you already know from practical experience, this cart is moving up the ramp, slowing down. At some point, it'll reach its apex, right? The highest point on the ramp, stop, turn around, and speed up down the ramp. And that's what you see here on the extended line, right? It eventually hits the x-axis here right around maybe 1.6 seconds and then starts to turn around and speed up in the positive direction. So that's what we're looking for in the verbal description, that you're saying moving up the ramp, right, negative direction, and then slowing down while doing so. Let's take a look at the FBD. I'm going to pause and draw it in. You see the free body diagram here. The two primary forces are the normal force and the weight. Notice that this free body diagram is true whether the cart is moving up the ramp, as it is in our data set, or a little bit later when it stops and speeds up down the ramp. Now you might have some friction in here as well. If you were drawing the free body diagram of the cart moving up the ramp, you'd have a little friction down the ramp, right? Or if you were drawing it for down the ramp, there'd be a little bit of friction up the ramp. But it's a low friction cart right from the lab, so we don't really need to add the friction. Let's move on to number four. Many of you surmised that to get the acceleration you had to calculate the slope, but you forgot your graphing basics right from the very first lab of the year, which is that anytime you calculate the slope of a line, you should pick two new points, not part of the original data set. Doing so yields an answer of around 1.7 meters per second squared. Please don't forget units. Remember that these numbers, unlike math class, correspond to something about the physical reality of the cart. In physics, you're constantly challenged to go beyond your math understanding and assign actual meaning to what those numbers are, right? And so remember that in this case, the slope's not just a slope of a random line, but it actually represents acceleration of the cart. Same goes for the next question, the initial velocity of the cart. I got many answers here of an initial velocity of 0. Now remember, when we say initial velocity, we mean initial velocity of the motion in question. Not like a long time ago when the cart was chilling out on the lab bench or the lab table. Of course, at some point earlier in time, it did have an initial velocity of 0. But for this cart to move up the ramp, I think you would agree with me that there's no way that its initial velocity can be 0, because if it were, it would just simply roll down the ramp. It would have nothing, no momentum up the ramp. You must give it initial momentum, which means you must give it initial velocity. That initial velocity is represented on your graph by the y-intercept. Now, I wasn't looking for this exact answer. I was looking for a y-intercept that corresponded to your y-intercept, right? For me, it's about 2.6 seconds. Excel told me that. Here's the y-intercept. All right. Let's look at the graphs. To do the graph, remember your verbal description. Moving up the ramp, so that's a negative direction, right? That means the graph must drop, and then slowing down means a flattening curve, right? A flattening curve. So we have something like this, right? Flattening curve, flattening curve. Eventually it actually stops, right, that we talked about, and then speeds up down the ramp. So that is the position time graph. Many of you struggled on this, so perhaps you need some review. Come in and try some on the idea walls before the test this week. For number 8, the acceleration time graph. Okay, that was much more straightforward. Many of you got that right. Flat line. And then the number here, right, because it did say to include vertical, horizontal, and vertical values, right? For that, I was looking for the number to correspond to whatever you got up here in number 4. So that number on the y-axis. Finally, we come to the equations of motion, which makes me wonder, okay, how many of you actually did the review? I think it really showed. If you got this right, you probably did the review, and if you didn't, you probably didn't. But remember that each of these coefficients, okay, each of these come from something of the graphs of the cart. So in this case, the y-intercept's the initial velocity, the acceleration a, and over here, position, initial velocity, and half the acceleration, right? Half the acceleration. So it's this line here that is the correct answer. That's what we were looking for. Okay, after you have completed this tutorial, you should come see me to do a little post-tutorial quiz. Thanks for watching.